All right, we're at section 20.3, the equipartition uh, of uh, equipartition of energy. And let me dismiss this so it doesn't interfere with the slides. Okay, so for when we get to diatomic molecules, we can see that the diatomic molecules indeed can have translation, as shown in figure A here, translation motion of the center of mass of this diatomic molecule. But we can also have rotational motion about the various axes. In particular, we're interested in the rotation about X and the rotation about Z. The rotation about Y, the moment of inertia is small, and uh, so the energy associated with the rotational energy around y is 1/2 I omega squared, and the I in the y direction is small compared to the other two, so we can dismiss it uh, if we uh, if we uh, look at it as particles. It's non-existent. So this having the diatomic molecule adds 2 more degrees of freedom. We have the uh, motion in the translational motion, and the X, Y, and Z gives us the 3 degrees of freedom. Well, here we get 2 more in the rotation around the X axis and the rotation around the Z axis. Um, and so that gives us uh, the internal energy is, since there's 3 translational directions, X, Y, and Z, gives us 3N, 1/2 kBT. Let's remember that each degree of freedom contributes 1/2 kBT of energy per molecule. So for the translation, we get 3N times 1/2 kBT plus 2N times 1/2 kBT for the rotational. Right now, we're ignoring vibrational. We'll get to that in a little bit. So we get uh, 5/2 NKBT, which is equal to 5/2 NRT. And so if we look at the, we get the 5/2 NRT. Now this, if we substitute that 5/2 NRT into the CV equals 1N over DE internal over DT, we get that CV is equal to 5/2 R, which is 20.8 joules per mole per Kelvin. And if we look at CP, which is equal to CV plus R, we're going to end up with 7/2 R, which is 29.1 joules per mole per Kelvin. And the gamma, which is CP over CV, is equal to 7/2 over R over 5/2. I'm sorry, it said 7/2 over R. 7/2 R over 5/2 R, which is equal to 7/5, which is equal to 140. And these are very close to the we'll show that table again. Those are very close in values. Now let's add the vibrational motion. This adds another degree of freedom. The energy, if we imagine this as 2 particles hooked together with a spring, we get vibrational motion along the molecular axis. That adds, more degrees of freedom. So we have 3N 1/2 kBT plus 2N 1/2 kBT plus 2N 1/2 kBT gives us 7 NKBT equals 7/2 NRT. And if we go through the same juggling that we did for CV, we get substituting the 7/2 NRT into the CV equation, we get that CV is equal to 7/2 R, which is 29.1 joules per mole per Kelvin. Now we can see that the at low temperatures, the diatomic molecules pretty much just look at like they're translating. As we get higher in temperature, we see the rotation, and if we get even higher, we see the the vibration. So you can see how it jumps from 3/2 R to 5/2 R to 7/2 R with increase in temperature. Now this notice that the horizontal scale is logarithmic. You can see the 10, 20, 50, 120, 500, 1,000, 25,000, 10,000. You can see that it's logarithmic. This is not logarithmic on this side. Okay, let's, and here's the table. You can see how there is a lot of agreement. When you get to polyatomic gases, there's a lot more vibrations and rotations and more degrees of freedom. So you can see how the CP jumps to much higher values. So let's, we'll talk about energy quantization, and there we get into energy levels, and this is more into, gets into a little bit of quantum mechanics. We're not going to touch on quantum mechanics this semester, but we can see you get vibrational states. You can see there's rotational states here between TA and TB. As the energy goes up, you get vibrational states, and the rotational states lie closer together in energy than do the vibrational states. So you can see that there's, with increased energy, you get these higher and higher states, energy states. And let's see. So in this portion, you see CV is equal to 3/2 R. In this portion, CV is equal to 5/2 R. And then in this portion with the vibration, you see that CV is equal to 7/2 R. Okay, let's look at a quiz. The molar specific heat of a diatomic gas is measured at a constant volume found to be 29.1 joules per mole. Well, let's go backwards and let's see where the 29, that's 29, that's up here. Well, okay, so we see that there's vibration, rotation, and translation. So let's look at this. The molar specific heat of a diatomic gas is measured at a constant volume and found to be 29.1 joules per mole per Kelvin. What are the types of energy that are contributing to the molar specific heat? Well, we saw it on the graph. There's translational, rotational, and vibrational. Sure enough, translation, rotation, and vibration. Okay, the molar specific heat of a gas is measured at a constant volume and found to be 11 R T. Well, the highest we studied was 7 R over 2. So the gas is most likely to be polyatomic. It has more than just, it's more than diatomic. It's got many molecules. And that's the end of 20.3.